Hello, today we'll be talking about singular value decomposition and its applications.
I'm Katie Keegan from Baldwin University.
I'm David Melendez from the University of Central Florida.
I'm Jennifer Zheng from Emory University. We would like to thank our supervisors and teaching assistants from summer at ISERM for helping us with this project, and we'll thank JMU for hosting this conference. So singular value decomposition is a really important matrix decomposition in linear algebra and has applications in many different fields. Today we'll be covering media processing, data analysis, and digital ownership protection. So first, what is the singular value decomposition? We have this matrix n by n matrix A, and we'll decompose it into three matrices. The left and right orthogonal matrices U and V. The columns are the singular vectors, and the diagonal matrix sigma, with each diagonal entry being the singular values in descending orders. As the rank of the matrix A is R, sigma R to sigma n are 0. An important property of the singular value decomposition is the Eckert-Young theorem. For this matrix A, we put it into outer product form, and the closest rank K matrix to A is the first K matrices added together, which we call the low rank approximation.
So black and white images can be represented pretty easily as a matrix. You just set everything as a gray value between 0 and 1, where I think 0 represents black and 1 represents white. Similarly, color images can be represented as the combination of 3 red, green, and blue matrices. So in order to compute the SVD, we can take these red, green, and blue channels apart, stack them on top of each other so as one tall, skinny matrix, and then compute the SVD of this combined matrix. So here's some examples that illustrate that using both the deterministic SVD algorithm as well as the randomized SVD algorithm. You can see that the performance is pretty much identical between the two, and that, as is illustrated in the log plot next to the original image, the low ranks approximations of the image still capture a lot of the dominant features of the original image. Another thing we experimented with was with modifying singular values. So that involves taking the singular value matrix out, this diagonal matrix, applying some modification to it, and just some mapping, like multiplying each of the singular values by some scalar, and then plugging this modified singular value matrix back into our SVD and seeing what the reconstruction looks like. So in the case of multiplying by some scalar, here were the results when applied to a cat photo. So for values that were greater than 1, we noticed that the image seemed like softened or brightened a little bit, whereas for values less than 1, the image was a little bit darker, but in all cases, a lot of the dominant features of the original image were still retained. And we also experimented with various other mappings, and these are all also applicable to audio and video matrices as well.
So for the next application we worked on, we applied SVD techniques to video background extraction. So the way we represent a video as a matrix is first we look at the video. It's represented as a sequence of pictures, which are called frames. What we do is we flatten each of these frames into a very tall one-dimensional, just a very tall vector, and we put each of these vectors into a matrix as columns. And this gives us our video matrix. If we take a rank 1 approximation of this video matrix, the vector that spans the one-dimensional column space of this rank 1 approximation is going to be the background of the video, as long as the camera is stable and the background is static. And so as an example, we took some security cam footage, one frame of which is visualized here. And we did a rank 1 approximation to extract the background, and that gave us this image right here. And so it actually works pretty well. And so next up, what we did is we applied SVD techniques to audio compression. And so what we do is we look at an audio signal, which is represented as a sequence of points sampled at discrete time steps from the waveform. So this is amplitude over time. And we want to transform this into a matrix in a way that still represents the structure of the data meaningfully. And we do this using what's called a short time Fourier transform. So the way this works is it's a method of time frequency analysis. So the matrix we get is going to have going to represent the frequency content of the image of the audio signal over time. And so what we do is we take small windows of the signal, we take a Fourier transform, we put the resulting frequency spectra into columns of this matrix, and we move this window over the signal over time and repeat. And so the result is a matrix where the horizontal axis is time, the vertical axis is frequency, and each entry is how much of that frequency is present in the signal at that time.
So here we have some demos for the low rank approximation of audios. This audio is rank 118, and the 25th rank approximation preserves the most components. Rank 5 still preserves the melody with only some slight more noise added. And we also apply the singular value modifications onto audios. We multiply each sigma by some scalar p, and the amplitude would increase along with p. Another application we did is onto data analysis. So we apply singular value decomposition onto the COVID-19 dataset provided by the USA Facts. Here's how our data matrix is going to look like. Each row is an observation, being a county or a state, and each column it's a date, with the number being the cumulative or new death cases or death or case numbers. Here's analysis over the cumulative known COVID-19 deaths each day. And this is for 50 states plus Washington, D.C. So we have 51 observations. And the date ranges from February the 6th to July the 5th, with February the 6th being the first day where a death case appeared in the United States. So here I plotted the first two singular vectors and the first three singular vectors. We can see that the four outliers are Washington, California, New York, and New Jersey. Washington is the state where the first case appeared, and California is the state where it was the most severe at the time during the range of her selection. New York and New Jersey are away from the clustering in the same direction but at different extent because they have the same pattern of the outbreak but with different severities.
So one of the major questions in the realm of digital ownership protection is how can we verify the owner of a piece of media, like an image or a song? So one way we can do this is by hiding a watermark inside this media using the SVD. So we have some concerns when designing such a watermarking scheme. We don't want the fact that we included a watermark to be perceptible. We also don't want anyone else to be able to extract a fake watermark and try to claim false ownership. And ideally, a watermarked piece of media should be able to undergo some distortions or some compression, and we should still be able to extract our watermark from the compressed media and prove our ownership. So just like how we saw earlier with how when the singular values are modified, a lot of the major characteristics of a piece of media can still be preserved, this property can be used to our advantage for watermarking. So one of the first watermarking schemes that does this is the Liu and Tan watermarking scheme. And the embedding process involves taking the SVD of the matrix you're watermarking, A, the SVD of your watermark itself, scaling the watermark by some value alpha and adding it into the singular values, and then using the matrices obtained above to create a watermarked piece of media, AW. And then you would save these matrices as your keys for the extraction process. And for the extraction process, given a potentially distorted watermark, AW tilde, and your keys for extraction, if you knew that the Liu and Tan watermarking scheme was used in the embedding process, then these two would be exactly the same. And then from there, you're just computing the embedding process backwards to obtain a potentially distorted watermark. So here's some examples of this process in action. You can see that for lower scaling values alpha, the effect of the watermark on the image is pretty much imperceptible, but for alpha equals 1, you can definitely see that something's different, but this comes at a sort of trade-off since lower scaling values make it more difficult to extract the image once a distortion has been applied.
And here we have some examples for audio watermarking. We embed the previous news audio as the watermark into the Bach cello suite. With alpha being 0.1, it's pretty much imperceptible, and with alpha being 0.4, it still mainly stays the same. And as we apply distortions, specifically, we lower the pitch of the entire audio, the extracted watermark still preserves the melody and most of the features. This proves that the Liu and Tan watermarking scheme is really robust.
So although the Liu and Tan watermarking scheme is robust to distortions, it turns out that it's actually a little bit too robust, and that comes at a cost to security. So the way we test security is using the security test that we'll outline here. So first thing we do is we embed a watermark W into an image to obtain the watermarked image. And then what we do is we attempt to extract the phony watermark from the image. So this phony watermark is a different watermark than what was actually embedded in the image. What we want to see is that when we extract the phony watermark, the image that is extracted is not recognizable as being the phony watermark. So what we see here is first thing we did is we embed this fox watermark into this raccoon image to obtain the watermarked image down here. If we extract the fox watermark from this image, then as expected, we get the fox watermark back, and that's the desired outcome. However, when we try to extract the phony watermark from this watermarked image, we get the phony watermark back completely unscathed. And so the problem here is that anybody can go and extract their watermark from any watermarked image and claim that they own the image, even though they didn't and their watermark wasn't embedded in there. So what we actually want to see is that this right here doesn't, that the phony extracted does not resemble the phony watermark, but here it does. So this watermarking scheme is not secure. So in an attempt to address this issue, Jain and some others proposed a modification to this watermarking scheme that's supposed to improve the security. And so the embedding extraction processes are very similar. The main difference is here in this step where we add a scalar multiple of this matrix to the singular value matrix of A. In the Liu and Tan scheme, we're adding a scalar multiple of the watermark. In the Jain et al. Watermarking scheme, we're adding a scalar multiple of the principal components of W. So this embeds partial information about W into A. And so in theory, you should need the complementary information of the right singular vectors of W to be able to extract the watermark from the image correctly. Another perspective is that we're actually just adding, if you work it out in the algebra, you're actually just adding a scalar multiple of this matrix here on the bottom to A. And so this perspective it will be useful for later. For extraction, it's very similar. You just apply this process in reverse and do some algebra and solve for the watermark. And so to give a visual of what this looks like, we embed this fox watermark again into this raccoon image. And we can see that even for low values of alpha, the watermark is quite perceptible in the form of these horizontal artifacts. We need to go very low to alpha equals 0.01 to be able to see, to be able to get the watermark not be perceptible. If we employ the security test again, embedding the fox watermark into the raccoon image and extracting the phony watermark, we can see that the phony watermark is not recognizable when we extract it. And that's the desired outcome, because this person who owns this husky watermark would not be able to claim that they own this raccoon image that they do not own. And so the security problem is actually solved for this watermarking scheme. We also test the robustness of the watermarking scheme to distortions. So here we embed the cat eye watermark into this coffee image, compress the watermarked image using a low rank approximation, and then attempt to extract the watermark from the compressed image. And as you can see, even for very low rank approximations, the watermark is still very recognizable. And so this is robust to distortions. In an attempt to try and remedy the issue with imperceptibility that we mentioned earlier, we proposed a modification to this Jain et al. Watermarking scheme that will solve this issue. And so this is the alternative perspective that we looked at before for the Jain et al. Watermarking scheme, adding a scalar multiple of this matrix. In our modification, what we do is we remove this pre-multiplied u from this additive factor. And this becomes our modified watermarking scheme. And so again, we're embedding the fox watermark into the raccoon image. On the top, you see what the watermarked image looks like in the unmodified version. And on the bottom, this is the watermarked image for the modified version. Now, as you can see, the watermark is much less perceptible in the modified version than it is in the unmodified version. Especially for alpha equals 0.01, it's hard to tell that there's a watermark embedded in the image. In an attempt to evaluate this mathematically, we compared the image to the watermarked image in Euclidean distance. And for the unmodified and modified versions of the watermarking scheme, the difference is actually exactly the same. However, if we look at the correlation between them, or the angle between them, if you consider them as vectors, the original image and the watermarked image, then they're actually much more similar in terms of this for the modified version than they are for the unmodified version. And so this shows us that the watermark is much less perceptible for the modified version of the watermarking scheme. Finally, here we can see that we employ the same security test and it still passes. So we attempt to extract the phony watermark and it gets all jumbled up. And so this person could not claim ownership and the scheme is still secure. Finally, here we can see on the bottom, if we try to extract a watermark from a distorted image, the watermark is still, it's not quite as recognizable, but it's still recognizable enough. So this is still somewhat robust to distortions. And so in summary, the singular value decomposition is one of the most important tools in linear algebra, and it has applications in all sorts of different areas of mathematics and science. We touched on a few of them here, including image processing, audio processing, video processing, data analysis, cybersecurity, and we also proposed a modified watermarking scheme that improved on some desirable properties. For the future directions, we want to look further into video background removal, into modern watermarking algorithms, into audio watermarking issues related to that, and watermark extraction using the randomized SVD. So if you'd like to look through some of our references, then I'm going to scroll through them here, and you can pause the video if you'd like to look at any of those. And that's it. Thank you very much.